I'd like to just take a moment to thank our partner, Charles Schwab. They've sponsored this entire series to help us make these events possible. When Chuck Schwab founded his company more than 40 years ago, he set out to challenge the status quo with a radical idea, that a business was here to support the people it served. This idea has been foundational to everything that Schwab has done over the last 4 decades. Similar to how the MIT Club of Boston encourages our members and alums to engage in lifelong intellectual and emotional partnership with MIT, Schwab encourages all clients to be fully engaged with their finances and own their tomorrow. Each consultant believes that being fully engaged results in better outcomes, and that's why they encourage you to ask tough questions, and they are here tonight to answer any questions you might have. There they are. Okay, so that's about all for me. I'd like to introduce our speaker, Vladimir Bulovic. He's the Fariborz Massey Chair in Emerging Technology. He's the MIT School of Engineering's Associate Dean for Innovation. He's co-director of the MIT Innovation Initiative and the NE-MIT Solar Frontiers Center, which is one of MIT's largest sponsored research programs. He leads the Organic and Nanostructured Electronics Laboratory, the One Lab, which he developed as a unique open nanotechnology facility. Research interests include studies of the physical properties of organic and inorganic nanostructured films and structures and their applications in novel optoelectronic devices. His academic papers have been cited over 10,000 times, and 60 US patents and patent disclosures have been licensed and utilized by both startups and multinational companies. He's a founder of too many companies to mention here. QD Vision, Cativa, Ubiquitous Energy Inc., and so many, over 200 employees in the US and a similar number of employees abroad. PhD from Princeton, and contributed to the launch of the Universal Display Corporation and Global Photonics Energy Corporation. He's a recipient of the US Presidential Early Career Award for Scientists and Engineers, National Science Foundation Career Award, Ruth and Jill Spira Award, the Eta Kappa Nu Honor Society Award, and the Bose Award for Distinguished Teaching. He's recognized as an authority in the field of applied nanotechnology, named to the Technology Review TR 100 list. And in 2012, he shared the SEMI Award for North America in recognition of his contribution to commercialization of quantum dot technology. On top of all of that, he is the Class of 1960 Faculty Fellow, honoring contributions to energy education. And in 2009, he was awarded the Margaret McVicker Faculty Fellowship, which is MIT's highest teaching honor. So a fellow of the World Technology Network and the Xerox Distinguished Lecturer in recognition of his continued contribution to innovation and practical applied nanotechnology. So I'd like you to join me in welcoming Professor Bulovic.
Thank you. It's an honor to be in front of you. MIT alums are an extremely distinguished crowd that has done tremendous things for the world. I think if you actually look at the statistics, you'll be probably not surprised to find out that about 30% of all the alums have in some way participated in startup companies. And actually, if you add up all those companies together, you'll realize that it's about 30,000 of them that they launched. That employ about 4.6 million people and are worth about $1.9 trillion. If you just look at the MIT alums and what they've done, they have essentially generated an economy of the size of Switzerland, a little bit bigger, number 10, if you actually count it that way, based on the technical prowess of what you're doing by launching new ideas beyond. The present students are doing their best to live in your image. Indeed, it is the generation that has graduated that is attracting the next generation of amazing students to join us. After all, when it comes to MIT as a business, the product that we have is really twofold: knowledge, ideas that we make, patents, papers, technical conferences we give talks at. But much better product we have is our people, people who change the world once they step out of the bounds of MIT proper, and indeed take on the true mission, which is to apply their knowledge that hopefully they gain a bit of at MIT and utilize the prowess of their skills, connections to their amazing colleagues from the days of being at MIT to think about what next the world needs. I had the pleasure of joining MIT in the year 2000, and I did see it as my institution, a place that I very much feel is changing the world today and is bound due to our commitment to what we need to do next to change the world again and again. A colleague of mine once said, it seems to be that our business is to invent what the next stage is, tell it to the world, and then move on and figure out what the next one is. There's a continuous drive, and that drive comes from our students. The hardest thing to do at MIT is to teach a lecture and try to finish it with, oh, and tomorrow I'll tell you the rest. You can't. You just can't do that. You can't tell me that you're not going to tell me today, in today's lecture, something that I can use tonight to invent the world in some other way. That is the drive that our students give us as we think about what is the next thing we need to give them. And so thinking about where MIT is today, clearly we live in a digital age, a place that has enabled us through the introduction of the internet and the way we use the digital technologies to completely transform the planet as we have it. But we also are at the dawn of the next age, what I refer to as the nano age. MIT technology and technology around the world indeed has enabled the existence of today's digital age. Today, roughly about 3% of the world's electricity is consumed by cloud computing. Anytime you look at your phone, you're using energy somewhere far away from your phone, right? Somewhere that needs to process all the data and then send you back the information. That's about 3% of US electricity today. The data processing and the need for cloud computing is doubling roughly every year. So what does that imply from 10 years from now? Well, the amount of electricity we'll need will increase. By how much? Well, by about 2 to the 10th power a decade from now. That's about 1,024 times more than today. And today is 3%, so multiply them out. It's about 3,000% of the world's electricity will be needed to run the digital infrastructure of year 2029. That's a lot of electricity. It took us about 150 years to make the present electricity capacity. I don't think we'll 30-fold increase it. And if we did, we'll have issues. What is the key to the next age of digital revolution is actually the hardware backbone that runs it. We can make electronics maybe 100 times more efficient. Maybe not use electrons, maybe use photons or excitons or plasmons or polaritons or exciton polaritons. These are quanta beyond the electron that indeed we know how to manage, but all those technologies down on the very small scale, nanoscale, are very much nascent. What I'm going to tell you as a way of thinking about how to tell you today about nano, I often can talk about electronics very easily, right? I mean, we can, as an electrical engineering professor, I can, not too many words, I can tell you that indeed today's transistors are very small. We pack 1 billion of them in a square inch or more. But that is obvious, I mean, to you. You have heard that somewhere else. Where else do you encounter nanoscale, right? Would be a good question to ask. And it turns out anything you've ever done, anything you ever sensed happens to be nano in size. I'll show you some of those images. I will start with electronics a bit first, but unusual electronics you might have not seen before. I'll think about the ways to think about imperceptible technologies that happen to be, due to the nanoscale properties of matter, allow you to make new types of devices that you might not ever have imagined are possible. Or maybe you imagined possible, you just didn't quite know how to do it. Well, let me show you some ideas. Now, what I'm going to show you is the tons of work that happened over the last couple of decades. I'll show you a fair bit of my own work, because I figured I'm standing in front of the alums. I want to give you not very broad pictures. I'll show that at the end. I want to give you a few insights, a few kind of deep dives, things that were able to be scaled because we had the persistence of exploring the nano world and then saying, well, what can that be used for? And how can that transform the way we think about the world? This image is of a technology that doesn't yet commercially exist. It's a piece of glass that, when optically illuminated, glows back at you. It's coated with quantum dots that are inkjet printed, in this case in the shape of the MIT seal. And it allows you to rethink how to make heads-up displays or indeed invisible displays, if that's what you wish to do. Let me spend a little more time with it a little bit later, because I would like to first of all show you just what happens when you get down to the nanoscale. Mind you, a nanometer, I know you know it, but I'll just repeat it for that because this is taped. A nanometer is 1/1000th of a meter. Take another way of putting it is if you look at the human hair, it's about 100,000 nanometers in width. So slice your human hair 100,000 times and you get yourself to the scale I'm going to talk about today. That scale happens to be inherent to everything we do. For example, if you take a chunk of gold or a chunk of silver and take that gold and silver and slice it down to the size of nanometers, maybe 5, maybe 10, gold and silver will not look like gold and silver anymore. What they'll look like in the case of gold are what those yellow and red vials are showing. Those are vials filled with liquid, like water or ethanol, methanol, and suspended in that liquid are nanoparticles of gold. If I make a nanoparticle of silver, a tiny chunk of stone, or in this case, a tiny chunk of a metal, that happens to be nanoscale in size, 5 to 10 to 20 nanometers, it will look like the vials on the right that contain nanoparticles of silver. Give blue and green pigments. What you're looking at is a plasmon resonance. Electrons that are swimming inside the chunk of silver that is that small feel very much confined and their energy levels change. As a result, the kind of light they'll be able to reflect back also changes. And the silver doesn't look silverish anymore, it starts looking colorful. This is a nanotechnology that was at our fingertips about 500 years ago. And we used it. The nanotechnologists of Middle Ages colored the stained glass, just this way. They would take gold and mix it with molten glass. And because grandma told them to add a little bit of horse's hair and cow's milk and do the right chant, wait just a few minutes and you'll get yourself a beautiful looking stained glass that will forevermore remain blue or red or yellow or green, whatever color you happen to have chosen to make by following that secret recipe. That's why stained glass windows don't fade. What they do is they contain nanoparticles of silver and gold embedded in the pane of glass. And as a result, that pane of glass reflects those colors forevermore. The use of nanotechnology, in this case the fancy word of plasmonic resonance of the matter, indeed is enabled by controlling that size of that nanoscale object. Back in the Middle Ages, we didn't know that. As a matter of fact, it's kind of surprising to me to realize this, but if you look through history, you can ask, what's the first moment humans observed a series of atoms bonded together on the surface of some sort of material? What's the first moment in time when we actually saw atoms, a picture of atoms, and how they lay in a real chunk of matter? Was it a century ago? No, it wasn't a century ago. It was in the 1980s. That's 30 years ago. We invented the very first microscopes to allow us to actually see nanoscale. But what do you think we did first time we saw these atoms? This happened at IBM Zurich, where a couple of fellows were using a very sharp metal tip and sliding it across the surface and realized the tip is being pushed back by the surface. What they were testing is essentially the roughness of the surface, and the roughness one was on the scale of atoms. This is known as a scanning tunneling microscope. And since the guys at IBM Zurich did it, of course the rest of us around the world wanted to do it as well. Throughout the 80s and into the 90s, we were making these microscopes just so that we can see the atoms ourselves. Because the pictures in the journals were wonderful and amazing, but we knew that if we can actually see the atoms ourselves on a particular surface we cared about, we'll discover science like we never saw before. This brings us to the end of the 90s. As a number of people around the world finally started seeing atoms as well. And Don Eigler over at IBM Almaden decided, why don't I start moving these atoms around and see if I can make these things called quantum corrals. Islands of atoms that could be arranged in perfect circles on metallic surfaces and confine the electrons within those corrals of atoms. Those quantum corrals provided these ripples, and these ripples was kind of looked like the way the ocean bangs against the shores and reflects back. What Don Eigler was looking at is quantum confinement of the electron C that's on the surface of every atom, confined by the atoms that he was able for the first time to position into these corrals. This is late 1990s.
So what do you do with that? Well, that brings you to the early 2000s, and you say, well, amazing science, amazing nanotechnology ahead of us. But all we did is just move one atom to the left, another atom to the right. It's not really practical, per se. Until roughly about 2012, where you start seeing organic light-emitting devices, molecular species that could be excited to glow and give you color, so-called OLEDs, organic LEDs. You now see them on your Apple phones, latest generations, or Samsung Galaxy phones, or Apple Watches. Those screens are made of molecules, 1 nanometer in size, that when electrically excited glow and give you color back. Depending on the molecule, you get different colors. Make reds, greens, and blues, and you got yourself a display. Pixelate it, and you got yourself a display. Nanoscale finally used. In a very direct fashion, what was the year? 2012, I believe I said. Yes. 7 years ago. We are at the dawn of the nano age. We're just beginning to understand how to control, thanks to the final insights to how things finally look down there. We're able now to finally control the nanoscale in ways to allow us to make multitudes of structures and devices that never existed before. So my goal for today will be to show you some of those examples. And I'll start with that organic LED. Here is a very useful way of using organic matter. A pickle that's been speared by 2 electrodes, and you apply 100 volts over it, and it's going to glow. This is 110 AC electricity. Now, if you slice the pickle very, very thin, you will avoid the high voltage, but you'll still maintain the high field. Apply only 5 volts over very thin slices of pickle, and you're going to get the glow back just the same. In organic LEDs, we don't use pickles. We use different kinds of organic molecules, but we only use about, well, let me see, about 50 molecules. And it's the middle 10 that are glowing, the middle 10 nanometers that are giving you the glow back on your screen. And from a pickle, you can now develop a $40 billion industry that has a position where it might displace the $120 billion industry of the entire display market. Why? Because OLEDs, very thin molecular films that can be electrically excited, can give you very different ways of thinking about how to make a display. Here's a video of another way of thinking of how to make that display. It's a regular phone, but maybe it has a particular feature where it can open up and give you a little bit larger display. Or maybe let's open it up one more time and give you an even larger display. Almost, you can think of it as a Z-shaped display that is able to fold. You might have seen, actually, something like this, just released by Samsung, if you read the news over the last month. Indeed, at Consumer Electronics Show this past January, it was featured, the first foldable, flexible phones. The one thing I have to tell you, though, about this particular video is that this video was made more than 5 years ago by an MIT startup called Katiba that envisioned the possibility of making these displays as long as we can manage the tool sets that are needed to make these displays and be able to give them to a million people. After all, the opportunities for OLEDs are amazing. They are remarkably good light-emitting surfaces. They are ultra-thin. They are thinner than a sheet of paper. As a matter of fact, they are roughly 1/100th the thickness of human hair is the thickness of the whole display. Your OLED display, when you pick it up, only weighs because whatever is a piece of glass or plastic that sits behind it. It uses very little power compared to all of the old technologies. And it has these advantages of having an incredibly high contrast between light and dark. It's super thin, ultra fast, pure color, curvable, with one slight challenge, which is that no one really knows how to make them. Because large area nanofabrication foundries simply don't exist. If you want me to make an X-silicon chip, I can do that very easily. Because someone before me spent 40 years developing really good foundries. If you start giving me an entirely new technology that never has been done before, please don't hold your breath, because it's going to take a decade to go from the first invention to a million people holding it in their hands. For OLEDs, it took about 25 years from the first invention to a million people holding it in their hands. many, many people in between making right choices in how to advance the technology. And indeed now, we are in a position where we really understand what does it take to make OLEDs. You start with a tool like this, and this is an old version of a tool that Cativa developed, a little startup. Started over in Building 13, and presently employing about 350 people over in their headquarters in Newark, California. They make tools. They have huge tool sets. One of their tools is roughly the size of the stage over here, maybe a little bit bigger. That's one tool. Because you need to handle very large pieces of glass to go ahead and make and print one of these displays. So here's an example of one of those machines, very much smaller version of their best one, moving and printing. That big gray box that's sliding laterally is a 1,000 nozzle inkjet printer that's able, with a 5-micron accuracy over 2 meter by 2 meter piece of glass, deposit tens of molecule thickness at a time. Now, how many of the pixels that they make can be bad pixels? I mean, how many of you are willing to buy a TV that has a few bad pixels? No?
You have no choice in the matter, they're there.
Well, that's true. That's true. It's just that it turns out, apparently, you can't really even sell a TV if it has more than one bad subpixel. You simply pull it out of the lot and make sure no one ever sees that one. That's a bad one. At the same time, if you buy yourself an iPhone or a laptop and you say, well, that microprocessor inside those machines, how many of transistors in those microprocessors do not operate at the expected performance level? The answer is about 10 to 20% of all your FETs are not where you expect them to be. So when you go ahead and buy yourself a laptop at an Apple store, let's say, and you have different options. You have the very fast machine, 2 gigahertz, let's say, and you have the 1.5 gigahertz, and you have a 1 gigahertz machine. No one intended to make the 1 gigahertz machine. That's the one that has a 2 gigahertz chip, but has a whole bunch of non-working transistors. And that's okay, because you slow it down, and it does the fine job still. You can't do that with displays. So if I'm going to launch a new electronics technology that's using semiconductors that have never been previously used over areas that are not 1 inch in size, but that are meters and meters in size, thicknesses that happen to be not microns in thickness, but actually in this case 10 nanometers with accuracy of about 1 to 2 nanometers, because otherwise voltage will be different, and make a technology that all operates with 99.999% yield, making sure that every one of those pixels is the same brightness to within 2%, because your eye can pick out 2% difference in brightness. Go ahead and launch the technology out of that. No challenge, no biggie, right? Well, I mean, if you list that list of challenges, no one would even in the rational mind ever step forward and say, I want to do this. But ask our students, and they'll say, are there any physical impossibilities to what you listed? No? Well, let's go. So it takes 8 years, but in their case, in Cativa's case, they indeed did launch technology. This is used widely across the industry. And every month now, there are about 100 million cell phones printed using this technology. Now they handle pieces of glass that are bigger. That's a human. That red frame is about 3 by 3.3 meter piece of glass. That's their biggest machines can handle that. And they have about, I didn't mention this, they have about 90 seconds to print over that entire area with the accuracy as needed, because you need to make sure you keep on churning through. If their machine breaks, $1 billion factory will be down. So it better last as well without breaking. These are big challenges, right? But challenges that are not unsurmountable if you invest time to building the foundries that can then allow the next and the next set of technology to flourish. Here's the technology that we thought we had everything sorted out back in 2005 when we started with. This is the technology of quantum dots, colloidal quantum dots, little chunks of stone that glow different colors depending on what size and chemistry of the dot happens to be. Brilliant, beautiful technology. It's the same quantum dots I used in the second image that I showed you, which was a printed MIT seal, inkjet printed to form the image. We wanted to replace OLEDs with quantum dot LEDs, electrically excited versions of quantum dots. We even made, in MIT labs, operational quantum dot LEDs. And we hold world records. We held, and others have indeed matched them and exceeded them, on the high quality quantum dot LED technology. Beautiful, brilliant, extremely sharp color, mesmerizing. And without a manufacturing tool set to actually give it to a million people. That is until now. Because what was needed was advancements of Katima to indeed enable us to think through how to make this technology. It's that co-innovation of the manufacturing tool sets together with the innovation of materials that in this case is just about ready to start propelling quantum dot LEDs as an item you might want to see in the next displays in about 5 years from now, I would imagine. It took about 30 years to get to this point, and the primary places where you might see quantum dots, initially it was to replace incandescent light bulbs. Well, why is that? Because the cool white LEDs are really cool, but really good efficiency, but not the right color. Your bananas don't look quite as ripe if you don't have the right light bulb shining on it. And we like the reddish color of the dim light. That's kind of reminiscent of a sunset that is redder. But you do not want perfect daylight in your basement because it's not the right brightness to match the daylight. You want dimmer, redder light whenever it's dimmer, because I'm guessing because the sunsets that you're used to seeing naturally are a little bit redder when the light is dimmer. So that light bulb doesn't look very good, the one in the middle, but if you go ahead and put a thin layer of quantum dots on that LED light bulb, you can provide me a color look that is exactly the same as that incandescent light. This then allows me to make a light bulb that is as efficient as an LED light, but with a color quality that's measured in so-called color rendering index. Anything bigger than 90 is imperceptibly different from an incandescent light bulb. And the efficiency is remarkable. That's about a factor of 5 better than an incandescent light, yet same color quality. And if you want to make a business out of it, all you need to do is take the light bulb, paint it with quantum dots, and sell it to me. Now, when the light bulbs of this kind, back in 2009, were $40, an LED light bulb, back then, you might remember, it made sense to have an addendum on top of it in the form of quantum dots, because if I charge 5% of the value of a quantum dot, I can still make a couple of bucks. Well, today, LED lights cost only a couple of bucks themselves. 5% of a couple of bucks is not very much. You really can't do very much with that in order to build a business. 10 cents a light bulb? I spend more just walking around the lab, carrying the actual amount of material to make this thing. So we needed to invent a different technology, although our light bulbs were really a big hit back in 2009 for about a year. Amazing stuff, still lasts, that have been running all around my home. They never die and have beautiful colors. It just didn't make sense to make it as a business. Unless you can give me a more expensive light bulb. So where are the light bulbs needed? Inside TV sets, inside LCDs. There is a big light bulb in the back. If I can replace the white light of the LCD with a quantum dot enhanced LED, what that means is I want to have an LED that emits a beautiful blue from the gallium nitride, a beautiful red from the quantum dot, and a beautiful green from the quantum dot. Sharp red, greens, and blues is all you need to make your eye see any color of the rainbow by mixing those colors. Except you want to have a beautiful sharp colors. Quantum dots enable that. And that is indeed why today, if you go and look around your Best Buy or wherever you choose to look for your best looking TV set, you can find Samsung selling so-called QLED technology, quantum dot enhanced LEDs. This is a technology invented through MIT work, developed by this little company called QDivision, and then acquired by Samsung back in 2016. Today, starting in 2017, through today, you can indeed look at QLED TVs and recognize there's yet another MIT innovation given to the public to go ahead and give you a visually stunning image. Just wait a few years, and you'll start seeing these things around your garden or around your home if you wish to have night lights. Rather than plug them into the wall, well, maybe you can just plant them and have them do their glow as they need, feed themselves or whatever else the plants choose to do. Professor Michael Strano's work looks at bioluminescent plants and asks questions of how can we change our environments. He's actually reading a book there, Paradise Lost, under the glow of, that might be, I don't know, kale or cabbage, I forget now. It is reminiscent of movies like Avatar that seem indeed fantastical, but we know how to do it. These are kinds of questions that only are beg to say, is it needed? What technology, what would this kind of technology transform if we had it at our fingertips? Let me show you another aspect of technology, and I'll focus just a little bit different, because like we just talked about plants, and plants survive because of sunlight. Let's just talk about sun for just a moment here. So sun itself gives us a lot of power. If you compare it to that little square on the upper left, that's the amount of power that we continuously need to run the planet Earth, about 16 terawatts. If you compare that to what sun gives us, it ratios is 1 to 10,000. So if I could for, let's see, in the course of a year, there's not quite 10,000 hours, but let's say almost 10,000 hours in the course of a year, if I could collect all the sunlight that is shining on planet Earth within 1 hour and convert it with 100% efficiency to electricity, I could run the planet for 1 year. That's a good ratio. And there's a little bit of conundrum there. First of all, I cannot have a 100% efficient system, I'm pretty sure. That means, let me go with 10% efficiency. 20 is achievable easily as well. Let me just make my calculation simple and go to 10%, which means I need about 10 hours of sunlight collected to run the whole planet for a year. Why don't we do that? That sounds like a great idea. Oh, well, it's all the sun that shines on the half Earth, half of the planet Earth during those 10 hours, right? So I just need to cover half of planet Earth with solar cells. I'll be perfectly fine. No? Well, again, let me scale this down a little bit more. So I needed 10 hours at 10% efficiency, half the planet Earth. How about I go to like 1% of planet Earth? Well, that's 1,000 hours. We have 1,000 hours of good sunlight in the course of a year. With 1% coverage, actually more like 0.5% of the planet, you should probably be okay. Is that a large enough area to cover? Or I mean, is that too large of an area to cover? No, it's not too large of an area to cover. Our cities consume right now about 2 to 3% of all of the land area of the planet. So just make sure your roofs have solar cells and you've got yourself a good solid thing to have to indeed help the planet collect the sunlight and run it. And indeed, this is the format that typically you will find solar. Is it that it's covering a field? Maybe it's on a residential roof, or maybe it's a commercial rooftop. And these are the primary ways of thinking how to deploy solar. I think, though, this misses, I know actually, this misses about 2 billion people on this earth who do not have ready access to grid electricity. Those individuals, if they want solar, they need to do something like this. Let me show you this image on the right. That's how you get your solar cell to your village. It's the last 10 miles, last 15 kilometers. That is the hardest thing about electrifying your village. If you don't have grid electricity, you also don't have a road leading to your village. And if that's the case, you don't really care about what is the efficiency of the cell. You really care about how many watts are you carrying on your back. Because there are only so many trips you're going to take. I would claim that the figure of merit that truly matters in solar world today is actually watts per kilogram. How much power can I get per weight that the solar cell weighs? Let's say I can give you a solar cell that weighs 10 times less than silicon, but it's only half as efficient. Is it a good trade-off? Well, yeah. In the same amount of weight, I can carry 5 times more power. That's a good deal. I'll electrify my village a lot faster than I could have without doing that. Now, where else would you find technology like this? Well, anywhere. If I had it, a lightweight cell, maybe I can indeed dress any surface I touch. Does it make sense to do that? Well, it does, because it turns out silicon is amazing. It's been doing really well for us. 90+% of all the solar cells made today are made out of silicon. And the cost is dramatically going down thanks to all the advancements. But silicon is an indirect bandgap semiconductor, those of you who are electrical engineers in the audience, which means it doesn't absorb light very well. You need quite a bit of it, compared to some other direct bandgap materials like quantum dots, or molecules, or perovskites. These are nanostructural material sets we now know how to handle thanks to the last couple of decades of making OLEDs and figuring out how to run them backwards. All that OLED is, right, is it takes electricity, pumps those molecules, and gives you light out. Well, run it backwards. Take light, absorb it in the molecule, and generate electricity. That's all it is. You would use materials with optimized band gaps, meaning that you absorb the right colors of light. So OLEDs are not the optimal band gap material, but the physics is the same. I just need to choose among the several million available organic compounds a couple that will give me good performance organic solar cells. That's one option. And I'll go ahead and thin down my device from a wafer size to this emerging thin film size, which is about a micron, or maybe half a micron. That's it. If I give you a very thick cell like the silicon wafer, there is a big challenge to it, which is that it's brittle. I need to make sure it doesn't bend, because if it bends, it will crack. So how do I do that? Well, in a silicon cell, what you will do is you will go ahead and add a thick piece of glass, about 4 millimeters in the back. You can't bend that piece of glass, and hence the solar cell of silicon sitting on the front will not bend and crack. That's good. No, it's good. But it also adds 50 pounds of weight, 25 kilograms. That's a lot of weight for the guy to carry to his village. If I can thin down my cells to the size of 1 micron, if you bend them, will they crack? The answer is no. It's kind of like us standing on Earth. We are too short to notice that the Earth is curved. So if you give me a very thin cell and you bend it, if it's too short to notice that it's being curved, just like us. You can get away with bendable, twistable, foldable type technologies because you're redefining the material set and thinning it down to the nanoscale, 500 nanometers of thickness, with active layers in the middle being 10 to 30 molecules. As a result, you can take a piece of paper and you can paint it with molecules and make what are called printed on paper solar cells. Where would you use such things? Well, if you're in the developing world, for solar irrigation, for solar umbrellas, so the street vendors would have a little light, maybe a little air conditioning or cooling down. A rickshaw that has a roof made out of this particular material would not tilt over. Today's rickshaws with solar roofs have very heavy top and are bound to being flipped because of the center of mass being so high up. These are options, right, that could be transformational for places that right now have no access to grid electricity. But you better make sure you can make this stuff in a high throughput fashion out of readily available materials. And one day you might be able to easily deploy it, just like when you cover the field, the big green monster to prevent it from getting soaked by rain. Right? I mean, that's what it is, a big roll that you might be able to unroll very, very simply. Here's a video of one of those paper cells made not quite 6-7 years ago, where we can shine light on it and use electricity to power a little electronic device. And then we can test it by feeding it to a laser printer just to make sure it can still survive the thermal cycle of the laser printer. We print it right on top of it. Go ahead and attach electrodes to it, shine light again, still works. The piece of paper is quite resilient because the cell itself is infinitesimally thin compared to our present technologies. All of the weight of that cell is in the piece of paper. The actual cell itself is infinitesimally light. So we ask ourselves, is it possible to just get rid of the paper and just make the cell? Paper is like 50 microns thick, maybe 75 sometimes. Can I get rid of all of it and just use a 1 micron thick saran wrap? We make our own saran wrap, 1 micron thin, and then we added a solar cell on top of it. If you do that, you can rest that solar cell on top of a soap bubble because it's infinitesimally light. It changes the way you perceive what solar technology could be. And I'll show you what we recently did. This is one of those things I can easily carry in my notebook, because it turns out that the intestinal light solar cell, it's remarkable. But you can poke it with your finger. It's only a couple of microns thick. It rips in no time. So what can you do? Well, you can laminate it on fabric. This fabric is 25 micron thick fabric. It's used in bulletproof vests. It's very strong. And that's your solar cell. Overall, it's about 100 times less weight than silicon. Its performance, no, I can't do 20% power conversion efficiency yet. But I'm pretty sure we'll get to 10% in not too long of a time. And 1/100th of the weight. How can you deploy your solar now? You wouldn't have to indeed reinforce your roof. You would simply take a roll of this and staple it to your roof. Or hang it as a curtain. Or use it as a sail or a ship, or whatever else you want to do with it. Wear it in order to go ahead and charge your phone as you're going along with it. You might not, though, be very fond of the color of my solar cell, right? You might be, fashion-oriented, with a keen eye for looks. At which point I would be hard-pressed to pass this particular version of myself to you, but I'll tell you, nanotechnology can enable you to get any look you wish by simply giving you an invisible solar cell. A solar cell that by design was designed not to absorb light that our eyes can see, the visible light. There's plenty of other light around us. Infrared light in particular is very abundant. So is ultraviolet. You can design molecules to prevent them from absorbing ultraviolet visible light and design them to absorb infrared and UV. As a result, you can make a PN junction solar cell made of molecules that looks nearly invisible. This is one version of it. And again, the model is UV and IR will be absorbed, visible light gets through. And here's a video of one of those cells, small version. This is a 4x4 inch, 10 by 10 centimeters, made by this little company, Ubiquitous Energy, started from MIT labs, that uses this piece of glass to power anything. You can have imperceptible technology around you. And as a result, you can completely redefine the way you think about, in this case, solar power. They've scaled it a bit. So last December, they showed me this image, which is a few of these panels put together. And last month, they showed me this image, which is their conference room, outfitted with dozens of these solar panels, prototyped on their prototyping line, one after the other. This is not something that we can still give to a million people yet, only because it takes money to actually build a bigger machine. However, you can imagine that with a technology like this, you can redefine the way you think about solar power. This is not a replacement for silicon. This is a replacement for technology that can sit inside an environment and be unobserved. And hence, is it on your glasses, so you can look through it, provide a few milliwatts for a Bluetooth radio or hearing aid, or is it on top of your Kindle, so you never, ever have to recharge your Kindle, or is it your building, so maybe you can offset a quarter or more of the electricity of a typical office building. That is the way we can think of it. Those are the things that indeed would enable you to rethink what the world can offer us. Go back. Oops. It will allow you to rethink what the opportunities are. And that allows me to get to the very end of what I want to tell you. I want to just give you a couple of more slides, and I'm looking at the time, on what the opportunities truly are. Solar indeed is one of those grand opportunities. When it comes to displays, of course, but anything else that touches you or that you use in everyday life could be redefined to the use of nanotechnology. That's why footsteps away from here is this building called MIT.nano. If you haven't seen it, please stop by. All of you being alums, all of you are alums, right? Anyone who's not? All right, I'm sorry to say, but your name is not in MIT.nano. But all the rest of you, your names are in MIT.nano. I'll tell you where you can find yourself. You're etched in stone forevermore. You and anyone else who was ever a student, a professor, actually anyone who was ever an administrator, anyone who was ever in a phone book of MIT between 1861 and 2018, is memorialized on the walls of MIT.nano. I'll tell you in a few minutes how. The building is located right at the heart of the campus. We made sure that no one has an office in it, no professor, for a very simple reason, because we don't know what is the leading discipline of nanotechnology, as nanotechnology itself is permeating everything we do. The simplest way to judge that is to ask, what are the present young faculty of MIT doing? Because they are the ones that are defining the future of what MIT is. And as a result, they are the ones that will need the tool sets to define the next several decades of work of MIT. I'll show you in a moment what those young faculty are doing. The building was placed for easy interaction. Anyone from any corner of the campus can come and use it. And all it is a shared space with a whole bunch of nanoscale tool sets. Tool sets that you couldn't afford as an individual to house in your own place, but as a community of upwards of 2,000 users, we can indeed support it. If you need a tool, you sign up for it, you pay a few dollars an hour, and you leave. We collect the money in the course of a year, and that pays for the staff and the upgrades of the tool. That's the model, as simple as that. If you're a friend of MIT, let us know. Stop by as well. If you're a person off the street who needs our tools, let us know. Stop by and we'll train. If you'd like to develop deeper partnerships, again, let us know. Stop by and use our tools. Our ability to make impact in the world is being able to engage. Use our tool sets as a way of engaging. After all, if you are trying to launch new innovations, it turns out there are very straightforward parameters you need to provide. One, bring people of different disciplines. Two, make sure they can easily meet each other. And three, make sure they can engage each other. What that means is make sure they can exchange ideas. You might remember your time at MIT as being a moment where you're drinking out of the fire hose. It was said many, many times over. That incredible moment of being able to be surrounded by peers that are unparalleled to other places you've had a chance maybe to see afterwards. And as a result, your ability to engage becomes seamless. You say, well, goodness, if I'm here in this incredible place, surrounded by these incredible people, I'm going to be open. I want to know what they know. They can teach me a tremendous amount of stuff. That is what MIT campus is. It's an extremely easy place to engage. And as a result, innovations, inventions flourish. MIT.nano was designed to extend that vision of what MIT is by building a space for all of us right in the middle of the campus. Roughly speaking, about a quarter of all of the people at MIT today have projects that are nanoscale related. That's a lot of people to work with. And as a matter of fact, if you go ahead and ask among the youngest of our professors, those who were just recently tenured, in a school of science, 51% of them use nanoscale to make discoveries. In a school of engineering, 67% of those who were recently tenured use nanoscale to make their discoveries in every field of engineering. So tell me, what is nanos about? Well, it's not about electrical engineering itself, although that is one aspect of it. It's about medicine and life sciences, because any molecule you ever consumed as a medicine is on the scale of a nanometer. Aspirin, ibuprofen, vitamin A, B, C, and D, all on the scale of 1 to 2 nanometers. Your DNA is 2 nanometers wide. For us to understand how does medicine interact with proteins inside our body, we need to see atoms on the scale of about 1 to 10 nanometers is the shape of some of these proteins. It's only very recently we have the tools to even see down to that level in a biological tissue, using what are now known as the cryo-transmission electron microscopes, tools that reside inside MIT.nano. You can go and see them, you can go ahead and use them. And as a result, we're able to explore the biology nanoscale like never before. The building itself consists of clean spaces. Those are the 4 levels right in the middle. The 2 tall levels, you can call them right in the middle. Clean spaces are clean rooms. Why clean rooms? Because nanoscale is small and the dust is like the boulder size compared to the nanoscale of our objects in the game. What's underneath? Imaging spaces. Basements are the quietest spaces you can imagine. Like vibration-wise, they don't wiggle in the wind. They are in a solid foundation. Very first thing we did is we poured 5 million pound slab on top of which to build these instrument rooms. surrounded every one of the rooms with quality range of aluminum to stop EM waves from penetrating in, then canceling the Earth's magnetic field with DC coils that surround that, maintaining temperature to always be the same to within 1 degree, and humidity to within a couple % in order to make sure that we don't disturb the experiments. And in the best of the rooms, we keep you out of the room. We keep you because of your humidity of your breath and indeed temperature of your body, you might disturb the measurements. So we'll keep you in the control room and the instrument is in the other room to go ahead and actually do the experiments. The building itself has everything that we right now know what is needed to allow us for the next 30 years to have a flexible space that can indeed grow as the time progresses with next and next discoveries. And I often think by year 2050, we'll master anti-gravity, we'll master quantum entanglement, and at that point everything changes. So in about 30 years, we'll change the tools of nano, but the building itself will stay still, meaning 150 years or more this building can stand, given the way it's constructed, to be forever flexible as we keep evolving. Down in the basement, you'll see one of these cryo-electron microscopes, and there's a protein imaged by a microscope like this that indeed tells you, teaches you about how matter is put together in the bioscale. Get up to the 5th floor, and you'll get to the prototyping facility where you can learn about how to translate those nanoscale discoveries into handheld objects. So you can raise money for your next startup. You know, is the VC going to give you money because you have a cool picture on a microscope? Or is he going to give you money because you have a handheld thing that does something? Well, do the translation into prototyping. Also on this floor is the very large chemistry teaching labs. Beyond that, we have an immersion lab. This is a virtual reality, augmented reality space. Well, why nano? Well, because one of those cryo-EMs generates about 2 terabytes of data every couple of hours. How do you handle the data? How do you see in 3 dimensions? Well, VR and AR can help you. But wait a second, beyond just seeing the data, what else can you do with a space like this? Well, maybe you can redefine education as we know it. Maybe you can redefine research as we know it. Those are opportunities that MIT.nano's immersion lab might offer you. Use it, stop by and figure it out. We have a series of companies that indeed help us out in supporting a place like this. You might imagine to actually run MIT.nano, it might cost a little money. And yes, we get a little bit from the users, a lot from the users, but still there's a significant amount of money missing at the end of the day. And that's where the companies like these provide to their annual membership an opportunity for us to complete the financial picture of the space. And much more importantly, provide us insights into what industry truly needs. If I want to deliver impact, we need to ask questions on what is really needed in this world. How do I find it out? Can I know everything? Well, it's much easier to have a friend in one of these places. And they become a friend the moment they join us. They are very welcome, and we spend many hours with them in order to ensure we understand their needs and we can inspire our researchers to work on those most salient problems, the ones that will truly be transformational for the industry. So I showed you a whole series of opportunities, and I promised you that I will share with you an image of your space, a place that you enabled for MIT.nano. So let me go ahead and show you that. This is a space like MIT.nano indeed, has many things that we need as researchers, but we also have a strong desire to engage community outside of the laboratories themselves. The way to really do so is to have community updates and meetings. June 6th was the day we received last year the certificate of occupancy. It meant the building is safe to walk into. And we'll let everyone walk through it, and then we closed it for a few months to make sure that everything works in it. Officially, we opened it again October 4th, where we had a big event. 1,000 people showed up, and if you had a chance to see it, I'm delighted you came by. Stop by again, because the building is changing every day. We are adding new tool sets and new opportunities, both inside the clean rooms and outside, in all the laboratory spaces. We spent time reaching beyond the bounds of what you would think we should typically do. Art and nanotechnology, really? Well, yeah. I just showed you that nanotechnologists of the Middle Ages used their nano skills to generate color for the stained glass windows. pigment that's coloring those chairs you're sitting on, I bet that's a 1 nanometer size molecule, because if it's bigger, it'd be dark like my pants. That's simply natural things. Nanoscale is what surrounds us. The texture of features we can feel 100 nanometer protrusions on the surface. We are surrounded by nanoscale. And the experience is an artist can actually allow us to go ahead and define it, if we can see it. Plenty of art dresses MIT.nano. If you're in the northwest corner of the building, you'll encounter the Northwest Passage, the artwork developed by Oliver Lassen, that's meant to symbolize the melting of the ice of the Northwest Passage. In the half circles of light reflected to full circles in those icebergs floating up there. Why they're there? Because you can see them from the clean rooms. So that you have a mission written for you. Make sure you save the planet. Because more of this will be happening. Because we didn't give anyone an office inside MIT.nano except for the staff to run the spaces, the building is occupied by a variety of public spaces you can enjoy. A lot of pretty places that you can walk through. And galleries. For example, on the first floor, there's a gallery, a digital one, organic LEDs, of course, make those screens. And one MIT art piece on the left. How many of you have heard of the one MIT art piece? A few of you. I'm delighted you did, and thank you very much for raising your hand. The rest of you who haven't, let me show you what it is. It's this picture of the MIT dome on the left that one of the visitors is taking a photo of. And if you zoom in a little bit closer, you realize that this particular picture consists of scribbles, of letters. And it turns out if you zoom one more level closer, you realize it consists of scribbles and letters that make names. Roughly speaking, 270,000 names that are anyone who ever was found in an MIT phone book between 1861, when we got founded, and 2018, when this particular art piece was completed. Of course, you will ask, what about the next generations of great individuals who join us? They'll be inscribed on the next version of this art piece that will be released in May, just for the graduation in 2020. And afterwards, every once in a while, we'll collect more names and relay it all out. So you can go to onemit.mit.edu and find exactly where your name is. Standing in front of that art piece, you can actually find it. You can zoom in with a phone, take a picture of the area, zoom into the picture, and you'll find yourself right there. The one thing that is not obvious here is that we took this image and then shrunk it to the size of 6 inches, and we etched it in a piece of silicon, a stone. So your name is forevermore etched in a piece of stone and mounted right next to this image on the right, onto the walls of MIT.nano. You are memorialized at MIT forevermore. Thank you very much for making our art piece. And with that, I'll thank you and encourage you to together we can build a better world. Any questions?
Any questions? Yeah.
I'll just shout.
Oh.
So I heard that you had to add about 50% to the capacity of MIT's power just for this one building. Can you talk a little bit about the engineering that went into building this?
So that's not quite correct, the statement you just made, which is that we have to add 50% of the capacity of MIT power to run this building. We are increasing the cogen plant capability of the MIT campus. MIT campus itself, our cogen plant provides all the heating and cooling, present one, the one before, as well as half the electricity of the campus needs. We knew that no matter what we built on this campus, we need extra power. We took the moment, we realized MIT.nano was going to disturb the campus quite a bit, and we decided to do everything at once. So we built, I mean, you might have noticed over the period of the last 6-7 years, there's a tremendous amount of construction on campus. MIT had, and this has been publicly released, we had about $2 billion deferred maintenance. We decided to fix that, but it takes a decade to do. And through that, we realized opportunities to further increase the energy efficiency of the campus. A cogen plant is 70+% efficient when it comes to burning something to make electricity and heat and cooling. So it makes a lot of sense to do that locally. And hence, why we gone ahead and did that. Now we are burning something, so to offset that fact, we also purchased a field in, I think, North Carolina that generates a large fraction of our electricity equivalent, and then provides it for the communities down there. Hence, trying to offset the fact that locally we don't have enough land to put solar, but hopefully we can offset that with the work that we provide elsewhere in the solar installations. The building itself is very energy efficient. That's the other thing to kind of point to, which is that we spent about 9 months considering about 120 environmentally benign options we can put in the building. And then we set a metric. We said, if I can spend $1 now, and in the course of the next 5 to 10 years, save that $1 in energy saving, I should spend $1 now. And the second metric we put forward is we said that a metric ton of carbon should be charged at least $100, not $30 or $40 like it's trading right now. So we said if we can spend $100 now to offset the metric ton of carbon over the next 5 to 10 years, we should spend $100 now. If you then look at 120 different options we had, about 60 to 70 of them made sense to do economically. Those are the ones inside the building. And we are tracking LEED Gold. We might be even better than that. Let me just say that we're looking really good when it comes to energy efficiency of a space like this.
So at the climate change conference last week, they talked about how the climate people are trying to keep global heating to something like 1.5 degrees C or maybe 2 degrees C. And in order to do that, you have to go up carbon within 30 to 60 years or so.
Yes.
And in order to do that, you need to build out energy generation capacity, like you mentioned, close to 1 or 2% of the world with solar. And then they talked about how to do that, you have to build out at a rate that's like 10 to 30 times faster than we are when we're building. Okay, that is, we're not coding the world of solar at the rate to achieve that percentage in that period of time. And with nuclear, you'd have to build like 100 nuclear power plants a year for 30 years to achieve these targets. So my question for you is, given all these numbers with energy generation, where do you think the planet's going over the course of the next 300 years?
I like a simple question, which is where's the planet going in the next 20 to 30 years? See, I think the very first place that we needed to develop, and I think I know there's a global consensus, the planet is changing due to what humans are doing. That's a big step forward in understanding. The next step is what are the obvious solutions we can implement. Solar has been actually accelerating in its growth about 40% annually. Last year it slowed down a little bit. I think it's only at 20% annual growth. Nevertheless, if you keep on projecting that, you'd realize that in another 15 years or 20 years, if you kept on growing at that interest rate, you would provide over 100% of all the energy capacity that the planet needs through solar. That's a fake thing to say unless I can add storage to it. A big challenge right now is figuring out how to store that solar energy that is being produced. Solar itself will keep on getting cheaper and cheaper and cheaper. Today you can buy solar electricity at 5 cents a kilowatt hour. There are power purchase agreements that are for as low as 3 cents a kilowatt hour. That's cheaper than any other technology out there when it comes to generation of electricity. Storage though is missing, and we need to figure that one out, and that's one of the urgent needs we need to add. Solar, the way I described it, would possibly provide us a way to transform the present production paradigms. You should be able to print as fast as printing newspapers, the next generation solar cells. But it's going to take 5 to 10 years to develop all the machines you need. Let me say 5 if we start investing right now. So that would be a possibility, right? But then storage really needs to be also met. In the meanwhile, our colleagues on Albany Street are developing the next fusion reactors. They believe that in the next 15 years they'll have that one figured out for the mass scale production. And that will be a tremendous game changer. Start with some hydrogen, make helium. In the case of power goes out, that machine is not going to blow up or anything like that. It will simply stop operating. So fusion itself in a portable format, portable meaning the size of this room, as opposed to much, much, much bigger, is likely going to come our way thanks to the inventions happening down the street here as well. There are options. We need to keep pushing in all of them in order to be able to indeed do good for the planet. There are some other very simple things we can do, right? I mean, we are indeed warming up. Well, we need to reflect some of that energy back. Well, how do you reflect it back? Well, there are a number of ways of thinking of it. One would be to say, can you coat, and this is one of those analyses you can do on the back of the envelope, can you coat the surface of the ocean that has dead zones, meaning it's too polluted to actually live life, but oceans are 90% absorptive of sunlight. Can you coat those with white floats or aluminum floats? Because that would change the albedo of the planet. If you did that, you could actually fix the extra heating we have right now. But it requires, deployment of floating platforms that are white or aluminum coated, right? These are not things to do today, right? I mean, there might be something to start considering today because the obvious way of how to truly deploy this is not in front of us. Secretary Chu suggested we should just paint every roof white. And if we did that, yes, we would change albedos of the cities, dramatically reducing the amount of energy that heats up the planet. There are options, but all of the technology we are developing, all of it, is only useful if it's going to be used. And success of a business is only about a quarter in the technology. The other 3/4 are in a way to scale it, in a way to build a team and a consensus to truly deploy it, and in understanding of the stakeholders who will be affected by my deployment, consequently losing business or losing jobs. So all those things need to fit just right. That's where the really hard problems are. I think the technology itself will keep on pushing. We'll try to make decisions for the next generation of those who need to make decisions on how to deploy our technology simpler by making it so obvious that this is the way to go because our technology is so much better. But unless the next step is taken, which is indeed adoption of these ideas, we won't get anywhere. It's a great question.
Yes, this is a little more down to earth. You started out talking about stained glass windows with nanotechnology and quantum dots. When I was at MIT, I was a film projectionist, and we were showing films on, using small grains of silver. Now it's the technology is being replaced, but if you were applying this type of quantum technology to something like motion picture film, would that maybe be something that could revive that type of technology, or bring new life into it, or is there? And what was your thoughts on that?
Yeah, no, the digital cameras are really, really, really good, and it is fairly hard to see us going back to the indeed film like we used to. You can make millions of pixels detection elements. To the point where I cannot really distinguish difference between an analog picture and a digital picture. Again, because there's so many detection levels are available behind every one of those millions of pixels. So I don't see it the same way that audiophiles really appreciate listening to the records because they might be able to distinguish the slight difference in the sound. Most of us can't, and hence we are perfectly happy with digital music as a way of recording it. The convenience, the compactness, the ease of distribution of the digital media really wins over. So I don't see it coming back. Unfortunately.
Yeah, quick question.
Yeah.
So you've talked sort of really at the macro level in terms of like solar and the impact of the environment and importance. And then all the way back to the stained glasses, like applications 1,000 years ago. What's really interesting and new and exciting today, like in that new building, in terms of like tools, like things you can do that just couldn't have been done before? Is it about manipulating at the nanoscale? Like what, in biotech it's like CRISPR and genome sequencing, right? So what is it in nano that's new from a tools point of view that lets you do things that just could not have been done before?
Yeah. It's a great question, and it's an answer that will take a while to really give you all the aspects of. The essence of it is that for the first time you can see how things look down here. And if you ask Phil Sharp, he says in structural biology, picture is not worth 1,000 words, it's worth 1,000,000 words. For the first time, you actually see the shape of these proteins and the way cells truly operate down on that scale. And as a result, as you're designing the next set of medicines, your information is much richer. You are actually making a keyhole and a key being the molecule, keyhole being the protein you're trying to attach yourself to that you could never see before. So to us, it's about seeing how things finally look down here. And through that, at the end, all you're really looking at is you're looking at some atoms, you're looking at some electrons, you're using electromagnetics and quantum mechanics to go ahead and start fathoming how the world looks out there. And then you start saying, oh wow, I can give you a more efficient optical switching elements and hence speeding up my quantum computation. Oh, I can do quantum computing now because I can finally understand that the particular qubit looks this way or that way. Oh, you know, I can go ahead and make a better battery because I realize that the dendritic growth that has been slowing down my battery operating times is due to the growth of these nanoscale objects that happen to accumulate. And I can in situ observe it because I finally have the tool sets to see that. When I'm growing a carbon nanotube or a nanowire of some other material, I thought that all that happens is that atom adds to the tube and then one more adds and then eventually it keeps growing and growing. No, actually we have now videos that show you that as you're growing carbon nanotube or one of these nanowires, I forget the exact material, is you're going to go ahead and have the wire grow and then all of a sudden, in a split second, a whole set of new atoms makes the next height. And wait a couple seconds, another layer comes in, and another layer, and another layer. That's a very different growth mechanism from anything we ever imagined before. How does that matter to us? Well, I don't know. Let's see. If I can think of controlling that nanoscale, I'll give you a device that doesn't yet exist commercially because we just came up with it not long ago. Today's electronics is limited by the so-called Fermi distribution of electrons. Everything obeys thermodynamics, and so electrons do as well. And so they're distributed in certain fashion across the energy levels that are available. This limits how quickly the transistor can turn on and off. The steepness of going from no current to a billion times more current, it can only happen at 60 millivolts per decade. So 60 times 9. 540 millivolts is the fastest you'll be able to have the on-off happen. That's because you're counting on the thermal distribution of electrons in the typical solid. What if instead you made the switch by having two chunks of metal that are 4 nanometers apart, and they're separated by a molecular spring, a molecule that's squishy. If I can squeeze those molecules, I can bring two metal electrodes from 4 to maybe 2 nanometers. If you did that and you applied 1 volt between those metals, you will get a billion times increase in current. Same technology as the switches we use right now in electronics, but not relying on the way the electrons are distributed in thermodynamics, rather relying on the Young's modulus squeeziness of your molecules. Well, how do you see that? How do you actually observe and design that? We have shown the first devices, by the way, to do this. And they do have very steep on-off ratios and do not use any semiconductors and yet give you the same function that we're expecting now at the energy comparable and speeds comparable to today's electronics without ever trying hard, right, to perfect like we're going to be trying hard with electrons. So there are many, many, many directions you can swing when it comes to thinking about what nanoscale gives you. But we finally, for the first time, have eyes on this scale. And with that, whole new list is open up.
Okay, time for one more question.
Yeah, if I went on Amazon tonight and I said I'm going to buy a nano-based product that I couldn't have bought 5 years ago, what would it be? What could I buy in 5 years?
Oh, excellent question. Well, you can buy shirts that don't wrinkle as much as they used to. Those are nanoscale fibers. You can buy pants that slip the ketchup off without you even trying because they're nanoscale coated. I'll show you a video of that happening if you want. You can go ahead and buy organic LED TVs. You can go ahead and buy medicine. That didn't exist before because finally we can actually see how it operates now on nanoscale. Nanoscale is in everything you touch. The taste of the ice cream is good because of the way that air bubbles of micron and nanoscale size happen to get introduced in the churning process of ice cream. And you know it because if you let the ice cream melt and then you try to refreeze it and you eat it then, it doesn't taste very good. Because you lost those voids, nanoscale voids inside your ice cream. Anything you've ever smelled, any molecule you've ever encountered your nose, each one of those molecules happens to be an object that is nanoscale in size. These are the molecules that make sense of lemon, orange, vanilla, raspberry. Compare them to benzene. They're all 1 nanometer in size. If they're any bigger, they will not be volatile enough to leave the surface of lemonade and reach your nose. Huh. It looks like your nose is filled into nanoscale detectors, and it is. You're designed to experience nanoscale, right? And if you can smell ethylene, you can smell the ripening of fruit. That's, by the way, what plants do. They smell each other. And that's when you have a greenhouse gap where you're growing tomatoes. When the first tomato turns red, flood the greenhouse with ethylene to tell the other tomatoes it's time to turn red. Wait a couple of days, they'll all be red, then pick them up, the vine. So if you can just detect the ethylene, it turns out you can save 15% of the produce of the United States. Because that's how much rots in our warehouses, because we don't know the crate of apples in the back is ready to be sold, because we cannot smell ethylene. Well, if you're C2 Sense, a little startup off the street here, they made paper detectors that use carbon nanowires, carbon nanotubes, and they're sensitized for ethylene, and consequently can give you pieces of paper that detect ethylene. Or if you're a Kripa, Ranasi, in mechanical engineering, you can make the most slippery surfaces ever. A company called Liquid Lab, just here towards Central Square, you can find them. They can take you, solve age-old problem on getting the last ounce of ketchup onto the ketchup bottle, because this is how typically things happen, but if you have one of their ketchup bottles, this is what you'll see. And the world will be saved. Opportunities are endless to use nanoscale. In this case, it's a nanoscale coating. It's edible if you choose to do so. I think the first things they've done is use it in Elmer's glue to get the last bit of Elmer's glue out. And a whole bunch of paint shops use it to allow mixing of paints without having to wash the watts in which the paints are mixed afterwards. You might think of de-icing planes this way. You might think of using the reverse of this and making an extremely sticky surface so you can spray the plants with it, and then, only then, spray pesticides. Because apparently 99% of the pesticides never stay on the leaf of a plant. They go into the soil and pollute it. If you can make stickier surfaces that are biocompatible, and with this you can, you might be able to go ahead and change the way we think about pesticides in our plants. There are many, many things that are nanoscale in your experience every day. You just don't really think of it that way. Detergents, there's another good one. There are 1 nanoscale objects that beautifully color your clothing. When you're buying whiter than white detergent, all you really are doing is cleaning your clothes and then dressing them with white phosphors that under sunlight glow and make your shirt whiter than white. I'll stop there because there are many more things to share. Thank you very, very much.
Official token of the club's appreciation.
Oh, thank you very, very much.
And I have one question though about the ultra sticky substances.
Yes.
Will I be able to get gloves that will let me just climb the wall like a gecko?
There was an undergraduate who used our nanofabs, micro-nanofabs, versus nano, and indeed he was a rock climber. He developed gloves that are extra sticky, gecko-like, just like you said.
Truly, we're making the world a better place. Thank you. And please join us for more